In classical fear conditioning, a neutral stimulus, conditioned stimulus CS, becomes associated with an aversive stimulus, unconditioned stimulus US, leading to the expression of a fear response even in the absence of the US. The amygdala has long been implicated in fear learning due to its role in associative learning and emotional memory. However, in human studies, amygdala activation during fear conditioning is often not observed, prompting researchers to hypothesize that amygdala adaptation or attenuation of its response over time could explain this phenomenon. So the objectives of the study: test the hypothesis of amygdala adaptation. The authors aim to assess whether amygdala activity over time, decreases over time during fear conditioning. Investigate the salience network. The study also explores how other brain regions associated with salience detection, like DAC and insula, respond during fear conditioning and whether they exhibit similar adaptation patterns as the amygdala. Examine network dynamics. By examining multiple brain regions in conjunction, the study tests whether changes in amygdala activity are coordinated with other regions in the salience network. So these are the three main objectives of the study. And now we're moving on to the methods. So participants, 18 healthy college students, 9 females and 9 males aged 17 to 33 participated in the study. Stimuli, the conditioned stimuli were Gabor patches, grayscale gradings with different orientations, used as CS plus paired with US and CS minus not paired with US. The unconditioned stimulus was a loud scream delivered through MRI compatible headphones. Paradigm: the experiment consisted of 3 blocks: habituation, acquisition, and extinction. 3 blocks: habituation, acquisition, and extinction. The acquisition phase included 120 trials where 25% of CS plus trials were paired with the US, which is probabilistic reinforcement, while the other 75% of CS plus trials were unpaired. Okay, CS minus was never paired with the US. In the extinction phase, the stimuli were presented again without the US to examine the decline of fear responses. Data collection: fMRI data were recorded using a 3 Tesla MRI scanner, and heart rate HR data were also collected to track autonomic responses. Okay. Key findings: amygdala adaptation. Over the course of the acquisition block, both responses in the amygdala attenuated decreased significantly, supporting the hypothesis that the amygdala adapts over repeated exposures to the CS+. This attenuation aligns with the idea that amygdala is involved in the initial acquisition of CS-US association, but as association becomes learned, its role diminishes and less neural engagement is required. Salience network dynamics. DAC and insula showed a similar decrease in activation over time, with early bold responses to CS+ being stronger compared to CS-, but both regions showing adaptation over trials. Representational similarity analysis (RSA) was used to track how voxel patterns in these regions evolved. As the conditioning progressed, the differentiation between CS+ and CS- responses in both insula and DAC decreased, suggesting a reduced salience of the CS stimuli over time as participants became more familiar with the contingencies. The authors proposed that this pattern of coordinated adaptation across the amygdala, DAC, and insula points to a large-scale reconfiguration of the salience network, implying that fear processing becomes more efficient as learning progresses, and these regions become less engaged in discriminating threat-related stimuli. Now, functional connectivity. The results suggested that activity in the amygdala, DAC, and insula was coordinated with similar temporal dynamics in the decline of bold signals. This supports the notion that these regions operate together as part of a salience network involved in processing of aversive stimuli. The study found that amygdala adaptation predicted both HR changes, autonomic response, and changes in representational dissimilarity in the insula and DAC. This suggests that autonomic fear responses and neural adaptation are linked in a coordinated manner. Representation of fear in the brain. So the RSA indicated that patterns of neural activity evoked by CS+ and CS- became increasingly less distinguishable in the insula and DAC over time, reflecting a reduction in neural distinctiveness. This suggests that as participants learned the CS-US association, their brains became more efficient at processing the stimuli, and fear responses became less pronounced as the CS+ lost its novelty. The amygdala, however, did not show such a clear change in pattern dissimilarity, possibly due to low signal-to-noise ratio (SNR) in the amygdala and insufficient voxel counts for analysis at the individual level. Now discussion. Amygdala's role in fear conditioning. The findings support that the hypothesis of amygdala adaptation, where amygdala activity initially increases with fear learning but diminishes once the CS-US association is established. This is consistent with previous findings that the amygdala mediates the acquisition of the CS-US association, but its role in fear maintenance may diminish over time. The attenuation of the amygdala responses over time could reflect habituation to the CS, a process where the threat becomes less salient as it becomes more predictable. Right. Now, the role of salience network. The study provides evidence that the salience network, amygdala, DAC, and insula, works together in processing fear-related stimuli. The coordinated adaptation across these regions suggests that they are part of a network that supports the efficient processing of threat, becoming less engaged as the CS becomes learned and less salient. These results suggest that salience network is not only involved in detecting threat, but also in adapting to predictable threats over time. This adaptation may be key to understanding how brain efficiently reallocates resources as the stimuli becomes more familiar. Now, implications for future research. The study design used a simple control set of stimuli, Gabor patches, which minimized potential confounds from more complex emotional or semantic associations. This allowed the authors to focus on basic fear learning processes Future studies using more naturalistic stimuli could reveal whether the observed adaptation dynamics hold true in more complex settings. The extinction phase, when the CS plus was presented without the US, was omitted from analysis in this study. Future work could incorporate extinction learning to investigate how the salience network adapts to both threat and safety cues over time. And in conclusion, the study provides more compelling evidence that amygdala adaptation during fear conditioning is part of a broader process involving the salience network, including DAC and insula. Over the course of conditioning, these brain regions show decreasing activation, which likely reflects a shift in neural resources away from processing threat as the association between CS and US becomes learned. The results underscore the importance of network level adaptation and fear processing, which allows brain to optimize its responses to familiar stimuli.